Harmonics and overtones. First, we're going to look at a vibrating string of length L, which is fixed at both ends. As it is fixed at the ends, there must be a node at each end. This is the simplest way the string can vibrate, with just one antinode in the center. At the next higher frequency that the string can possibly vibrate at, it must still have a node here, but now it also has a node at the center and must have a node at the other end. This is the next more complex situation that the string can be in. Getting more complex still, we have this situation. A node at the end, now two nodes in the center, and must again have a node at the other end. There must be nodes at the end, as the ends are fixed. This is the lowest frequency the string can possibly vibrate at. We call it the fundamental frequency. We can also call it the first harmonic. This is the second frequency the string can vibrate at, and we call it the second harmonic. But we can also call this the first overtone. Here we have the third harmonic, the third frequency the string can vibrate at. This would be the second overtone. We could go on with the fourth harmonic being the third overtone, and so on. But you'll see that the first harmonic has one antinode, the second harmonic two antinodes, the third harmonic three antinodes, and so on. The distance from one node to the next is half a wavelength, as is shown here, with wavelength as usual being represented by the letter lambda. So here L is equal to lambda over 2, or the length is half the wavelength. Here lambda over 2 takes us to half L, and so we have that L equals 2 lambda over 2, or L equals lambda. We have one complete wave within the length L. This now is our lambda over 2, and we have 1, 2, 3 lambda over 2's within our length L. So we can write that L equals 3 lambda over 2. Now to look at a column of air vibrating in a pipe which is closed at one end. The air will set up a longitudinal wave with the particles vibrating like this. At the closed end, the air will be unable to vibrate, so we must have a node. At the open end, the air is being caused to vibrate, so we must have an antinode. One way of representing this is to draw lines like this. Now this looks a little like a transverse wave, but if you imagine it as showing maximum displacement of the air particles at a point, so for example here they have no displacement to the left, no displacement to the right, for example, whereas here they have maximum displacement to the left, maximum displacement to the right. This then is the simplest way the air can vibrate, with just one node and one antinode. A more complex situation would have a node at the end. The air cannot vibrate here. An antinode at the open end, where we must have maximum vibration, but now also another node and antinode in the center. We can represent this with this type of line, where it is showing zero displacement here, maximum displacement left and right here, zero displacement here, maximum displacement left and right here. You must remember these are longitudinal waves. This curved line is simply representing the level of displacement left and right of the air at a point. The third, more complex situation would have a node at the closed end, an antinode at the open end, but now two sets of nodes and antinodes along the length of the pipe, represented by this displacement line. Zero displacement here, maximum displacement left and right here, and so on. This shows the lowest frequency that is possible in the column of air, so we call it the fundamental frequency, or the first harmonic. This is the second frequency allowed in the column, so it is the second harmonic, or the first overtone. This then is the third harmonic, or second overtone. Now, as the distance from a node to an antinode is a quarter of a wavelength, here L, the length of the pipe, is equal to lambda over 4, 1/4 of a wavelength. Here we've got 1, 2, 3 quarters of wavelengths, so L is equal to 3 lambda over 4, 3/4 of a wavelength. And here we have 1, 2, 3, 4, 5 quarter wavelengths, and so L is equal to 5 lambda over 4. Now to look at a column of air which is open at both ends. And so we must have an antinode at this end, an antinode at this end, the simplest situation giving us one node in the centre. We can represent this with the displacement line here, showing maximum displacement left and right at the ends, zero displacement in the centre, maximum displacement left and right at this end. The next more complex situation would have an antinode at this end, an antinode at this end, but now two more nodes with one antinode in the centre. The displacement line shows us this. The third most complex situation, or the third frequency up, would have an antinode at either end. The ends are open, so there must be antinodes, but now three more nodes and two more antinodes along the pipe, giving us this situation. This gives us the lowest frequency allowed in the pipe, or the fundamental frequency, which we can call the first harmonic. This gives the next frequency up allowed in the pipe, or second harmonic, which we can also call the first overtone. This is the third frequency allowed in the pipe, or the third harmonic, which we can call the second overtone, and so on. Remembering that the distance from an antinode to a node is a quarter of a wavelength, here we have 1, 2 quarters, and so L is equal to half of lambda, or L equals lambda over 2. In this case we have 1, 2, 3, 4 quarters, or a complete wave, and so L equals lambda. In this case 1, 2, 3, 4, 5, 6 quarter wavelengths, so L equals 1.5 lambda, or L equals 3 lambda over 2. With these situations, they seem to look very, very complicated, but all you need to remember is whether there are nodes or antinodes at the ends of the string or pipe. With the string, it is fixed at the end, so there must be no displacement or a node. With the pipe, if it is open, there will be maximum displacement or an antinode. If the pipe is closed, the air will be unable to displace, and so there will be no displacement, or a node.